All right, let's talk about a piece of technology that's not just an upgrade, it's a fundamental challenge to the way we think about computing, especially for AI. This is the story of a truly giant chip that's taking on an industry titan. Okay, so to get why this is such a big deal, you have to understand the problem. When you train a massive AI model today, you can't just run it on one computer. No way. You have to split the job up in all these ridiculously clever ways. Think of it like a giant chaotic assembly line. You've got different teams working on different parts of the car all at once. That's what this chart is showing with things like data and pipeline parallelism. And as you can see, trying to get all those teams to work together perfectly is becoming a distributed computing nightmare. It's just getting way too complicated. So here's the bottom line. AI models are hitting a wall, a memory wall, and a complexity wall. But what if, instead of trying to coordinate thousands of tiny brains, you could just build one, single, enormous one? Could the answer really be a single chip the size of a dinner plate? That question brings us right to our first section, the AI scaling problem. Here's the core issue, right? The hunger for more computation is growing way faster than what individual chips can handle. A model like GPT-3 needs something like 700 gigabytes of memory just to hold its parameters, its weights. Your top-of-the-line GPU, it has a tiny fraction of that. So the only solution has been to string together thousands of them, creating these hugely expensive and incredibly complex clusters. At that point, you're not just fighting a compute problem anymore, you're fighting a data logistics and communication problem. It's a mess. So if the current path just leads to a dead end, what's the alternative? Let's move on and meet the challenger, a radically different kind of chip. And here it is, the Cerebras CS-3 system. Now what you're looking at isn't just another server rack. Each one of these units is basically a single massive computer built around a single massive processor. This isn't the scale-out approach of just adding more and more little things together. This is scale-up, building one thing that is just vastly more powerful. Okay, just take a second to really let these numbers sink in. Look at the chip size. The WSE3 is over 50 times larger than NVIDIA's H100, which is the best they've got. AI cores, it's not even a fair fight. 900,000 versus 17,000. And then you get to the transistors. 4 trillion. No, that's not a typo. This isn't just a bigger chip. It feels like an entirely different species of hardware. So how on earth do you even make a 4 trillion transistor chip work? Well, that brings us to the real secret sauce, the core architectural innovation. Section 3, decoupling compute and memory. This slide right here, this shows the fundamental shift in thinking. On the left, you have the GPU way, the old way. It tightly ties compute and memory together. The whole model, or at least a big piece of it, has to physically fit inside the GPU's onboard RAM. That right there, that's the bottleneck. The Cerebras way, on the right, completely blows that up. It says, forget that. Let's put all the compute on this giant wafer, and we'll keep the model's parameters in a separate, massive memory pool, and we'll just stream in the bits we need exactly when we need them. This whole technique is called weight streaming. By ripping the model's storage away from the compute units, the size of your AI model is no longer limited by how much memory you can physically cram onto a single chip. You can just make the external memory cluster bigger or smaller as you need. This completely changes the game for training absolutely gigantic models. And this little icon does a brilliant job of showing you the concept. Instead of trying to hold the whole model in memory, the WSC just processes one layer at a time. The weights for that one layer get streamed onto the wafer, the computation happens all at once across its 900,000 cores, and then the results just flow out ready for the next layer's weights to stream in. It's a data flow architecture, not a data storage architecture. It's a huge difference. Okay, so the architecture is really clever for sure, but does it actually deliver? Let's get to the good part in section 4 and see the performance payoff. 210 times. Just let that sink in for a moment. In a study by researchers from Rice University, a Cerebras system was 210 times faster than an NVIDIA H100 GPU. And this wasn't some theoretical benchmark. This was for a real, complex scientific simulation for figuring out carbon capture. A speed-up like that doesn't just make research faster. It completely changes the kinds of questions scientists can even dare to ask. And what about sheer scale? Well, the WSE3 system is designed to support models with up to 24 trillion parameters. To put that into perspective, the biggest models out there today are in the low trillions. This isn't just about training today's models faster, it's about making a whole new generation of models possible, models we can't even build right now. But look, achieving these kinds of breakthroughs means you have to solve some of the hardest engineering problems on the planet. So let's peel back the cover in section 5 and just appreciate the engineering marvel behind this thing. First off, you gotta realize this isn't some one-off experiment. This timeline shows that Cerebras has been iterating at an absolutely blistering pace. They doubled and then nearly doubled again the transistor count in just 5 years. That shows a relentless, aggressive push on the technology frontier. That's what you have to do if you're serious about challenging a giant like NVIDIA. So, to build a single chip from an entire silicon wafer, they had to overcome these just monumental hurdles. First, you've got yield. On a 300mm wafer, defects are just a fact of life. They solved this with massive redundancy, basically building backup cores right into the wafer. Then packaging. You can't just stick this thing in a normal chip package. They had to invent a whole new way to mount the wafer to a circuit board. After that comes power. I mean, how do you deliver over 20,000 amps of current evenly, not from the sides, but vertically, right on top of the wafer? And finally, thermals. This chip puts out 20 kilowatts of heat. That required a totally custom high-performance water cooling system built right into the machine. And here's one of my favorite little details. It's just so clever. On a normal wafer, you have these scribe lines, right? They're basically empty streets between the chip designs where they'll eventually cut the wafer. Well, Cerebras repurposed that dead space and turned it into a super high-bandwidth communication fabric, wiring all the sections together. This creates an on-wafer network with unbelievably low latency, something that's just impossible when you're connecting separate chips with external wires. So, they've solved these absolutely insane engineering problems to create a totally new class of machine. What does this all mean for the big picture? Let's zoom out in our final section, the future of computing. What we're really seeing here is a clash of two fundamental philosophies. On the left, you've got scale-out. It's been the dominant approach for decades. You want more power? Just add more individual computers to the network. It's flexible, but as we saw, it creates this immense software complexity. On the right, you have scale-up. You get more power by building a single, bigger, faster machine. The hardware problem is monumentally difficult. But if you can solve it, the software problem becomes dramatically simpler. And that leaves us with the big question. Is the future of AI going to be built on these vast, distributed armies of GPUs, each solving a tiny piece of the puzzle, or will it belong to monolithic giants, single, massive processors that can just tackle the whole problem at once? The answer to that is going to define the entire next era of artificial intelligence.